When James Webb Space Telescope pointed its instruments at Pluto in late 2023, NASA scientists thought they were conducting a routine observation of a well-studied dwarf planet. What came back in the data shocked them. The images and spectroscopic readings revealed something about Pluto that nobody predicted. And it's forcing astronomers to rethink everything they thought they knew about frozen worlds at the edge of our solar system. What you're about to see isn't just another space discovery. This is a complete game changer, and by the end of this video, you'll understand why some scientists are calling this one of the most important observations James Webb has made since it launched. Look, I know what you're thinking. We already visited Pluto, right? New Horizons flew by in 2015, took those incredible close-up photos, and we thought the book was closed on the dwarf planet. So why is James Webb looking at it again? And more importantly, what could it possibly find that a spacecraft flying right past it didn't already discover? That's exactly what we're diving into today. And trust me, the answer is way more fascinating than you'd expect. Before we get into the mind-blowing details, do me a favor and hit that subscribe button right now. Here at the Space Frontier, we break down the latest space discoveries in a way that actually makes sense. And we've got some absolutely insane videos coming up about what James Webb is finding on Neptune and beyond. You're not going to want to miss those. All right, let's get into this. So here's the thing about Pluto. Ever since it was discovered back in 1930, it's been this mysterious little world sitting out there in the darkness, billions of miles from the sun. For decades, we could barely make out any details. Even our best telescopes just showed it as a fuzzy dot. Then came New Horizons, the spacecraft that took 9.5 years to reach Pluto. And when it finally got there in July 2015, it blew our minds. We saw mountains made of water ice as hard as steel. We saw that giant heart-shaped glacier called Tombaugh Regio. We saw atmospheric haze, possible cryovolcanoes, and a world that was way more geologically active than any frozen rock that far from the sun had any right to be. After New Horizons, scientists thought they had Pluto pretty well figured out. But here's what they didn't account for. New Horizons took pictures. Amazing, beautiful, high-resolution pictures, but pictures nonetheless. It captured visible light, the same kind of light our eyes see. James Webb? James Webb sees something completely different. James Webb. Space Telescope doesn't work like a normal camera. It's an infrared observatory, which means it detects heat signatures and chemical compositions that are completely invisible to the human eye. When Webb looks at Pluto, it's not taking snapshots. It's doing spectroscopy, breaking down the light into its component wavelengths and reading it like a chemical fingerprint. And that fingerprint is telling scientists something absolutely wild. Pluto's atmosphere is behaving in ways it shouldn't. Its surface chemistry doesn't match the models. And the temperature variations across the dwarf planet are creating patterns that challenge our fundamental understanding of how these distant worlds work. Let me explain why this is such a big deal. Pluto sits out there in the Kuiper belt, about 3.7 billion miles from the sun on average. At that distance, it's receiving almost no solar energy. The surface temperature hovers around negative 375 degrees Fahrenheit. That's so cold that nitrogen, which is a gas here on Earth, freezes solid. Methane freezes. Carbon monoxide freezes. Everything freezes. And because it's so far away and so cold, scientists assumed Pluto's atmosphere would be relatively simple and predictable. Just a thin shell of nitrogen with some methane mixed in, gradually freezing and sublimating as Pluto moves along its elliptical orbit. But when James Webb analyzed Pluto's atmosphere using its near-infrared spectrograph, something didn't add up. The atmospheric composition was changing in ways that the models didn't predict. There were chemical signatures that suggested active processes happening right now, not just frozen remnants of ancient geology. Now, you might be wondering, what kind of active processes could possibly be happening on a frozen ball of rock and ice billions of miles from the sun? That's exactly what has scientists scratching their heads. One possibility is that Pluto has some kind of internal heat source that we didn't fully appreciate. Maybe radioactive decay in its core is generating more warmth than we thought, driving a kind of slow-motion weather system in its thin atmosphere. Another possibility is that the interaction between Pluto's surface ices and solar radiation, even at that extreme distance, is creating chemistry that our models simply didn't account for. But here's where it gets really interesting. James Webb detected variations in methane and carbon monoxide distribution across Pluto's surface that don't match what New Horizons saw. And we're not talking about small differences. We're talking about significant changes in just 8 years. Think about that for a second. Pluto takes 248 Earth years to orbit the sun once. It moves incredibly slowly through space. Its seasons last for decades. The idea that its surface chemistry could change noticeably in less than a decade is shocking. It suggests that Pluto is far more dynamic than we ever imagined. New Horizons gave us a snapshot, a single moment frozen in time. James Webb is giving us the full chemical story, and that story is revealing a world that's actively evolving. The surface ices aren't just sitting there. They're sublimating, redistributing, reacting with a thin atmosphere, and possibly being replenished by processes beneath the surface. This isn't the dead, frozen rock we thought we were looking at. This is a living, breathing world in its own strange, slow-motion way. And here's another thing that has scientists talking. When James Webb measured the thermal signature of Pluto's surface, it found temperature variations that don't line up with the topography we see in New Horizons images. There are warm spots, relatively speaking, in areas that should be uniformly frozen. There are cold spots where we'd expect more solar heating. This suggests that Pluto's surface isn't thermally uniform. Different materials are absorbing and radiating heat differently. And some areas might have subsurface structures, maybe even pockets of warmer material beneath the ice, affecting the surface temperature. Remember, on Pluto, warm is still hundreds of degrees below zero, but even a difference of a few degrees matters when you're talking about chemical processes at those extreme temperatures. So why does all of this matter? Why should we care if Pluto's atmosphere is a little more active than we thought, or if its surface chemistry is changing? Because Pluto isn't alone out there. The Kuiper belt, the region of space beyond Neptune where Pluto orbits, is filled with thousands of similar objects. Dwarf planets like Eris, Makemake, Haumea, and countless smaller bodies. If Pluto is more active and dynamic than our models predicted, then chances are all of these other worlds are too. That means we've been fundamentally underestimating the complexity and activity of the outer solar system. These aren't just dead chunks of ice. They're active worlds with their own atmospheres, surface processes, and possibly even subsurface oceans in some cases. And if that's true, it opens up entirely new questions about where life could exist, how planetary systems evolve, and what happens in the cold, dark regions of solar systems everywhere in the universe. Now let's talk about the elephant in the room, or maybe I should say the dwarf planet in the room. Ever since 2006, when the International Astronomical Union reclassified Pluto as a dwarf planet, there's been this ongoing debate. Should Pluto be a planet or not? And honestly, most scientists moved on from that debate years ago. The definition was made. Pluto didn't meet the criteria because it hasn't cleared its orbit of other debris, and that was that. But here's the thing. These new James Webb observations are reigniting that conversation, not because they changed the technical definition, but because they're revealing just how complex and planet-like Pluto really is. When you've got active atmospheric chemistry, dynamic surface processes, geological activity, multiple moons, and a complex interaction with the solar wind, it starts to feel a little arbitrary to say this isn't a planet just because there are other objects in similar orbits. I'm not saying the definition is going to change tomorrow. The IAU has their criteria, and scientifically, there are good reasons for those classifications. But what James Webb is showing us is that Pluto deserves respect as a complex, fascinating world regardless of what we call it. And more importantly, it's showing us that we need to pay attention to these distant dwarf planets because they're teaching us things we never would have learned otherwise. Before I go any further, I want to ask you something. Do you think Pluto should be considered a planet again? After seeing what James Webb is discovering, does it change your perspective? Drop your answer in the comments below. I'm genuinely curious what you all think. And let's get a real conversation going. Team Planet or Team Dwarf Planet? Let me know. All right, so let's get into the technical side of how James Webb is actually doing this. The telescope has 4 main instruments. But for Pluto observations, the most important one is the Near-Infrared Spectrograph, or NIR spec. This instrument splits light into its component wavelengths, kind of like a prism splitting sunlight into a rainbow, but way more precise. When sunlight reflects off Pluto's surface and passes through its atmosphere, certain wavelengths get absorbed by specific molecules. Methane absorbs certain infrared wavelengths. Nitrogen absorbs others. Carbon monoxide has its own signature. By measuring exactly which wavelengths are missing or reduced, scientists can figure out what chemicals are present and in what quantities. It's like chemical detective work at a distance of billions of miles. What makes this so powerful is the sensitivity. James Webb can detect incredibly faint signals, which means it can pick up on trace chemicals that other telescopes would miss entirely. And because it's observing in infrared, it's seeing thermal information, the actual heat signature of Pluto's surface and atmosphere. This is data that New Horizons, even flying right past the dwarf planet, couldn't gather with the same level of detail because it had different instruments designed for different purposes. New Horizons was built for imaging and particle detection. James Webb is built for spectroscopy and deep chemical analysis. Together, these 2 missions are giving us a complete picture of Pluto that neither could provide alone. And that's exactly how modern space science works. It's not about one mission replacing another. It's about different tools working together to build a fuller understanding. Now here's something that really gets me excited. The atmospheric data that James Webb is collecting isn't just a one-time snapshot. Because the telescope is in space and can observe Pluto over extended periods, Scientists can actually watch how the atmosphere changes over time. They can track seasonal variations as Pluto slowly moves along its orbit. They can see how the atmosphere responds to changes in solar radiation. They can potentially even detect weather patterns if they exist. Imagine that, weather on Pluto. Not rain or snow like we experience on Earth, but the movement of nitrogen frost, the sublimation and redeposition of methane ice, the slow drift of atmospheric hazes. It's an alien kind of meteorology, but it's meteorology nonetheless, and it's happening on a world we once thought was completely static. This brings up another fascinating point. When New Horizons flew by Pluto, it had just a few hours in close proximity to gather data. It was moving at over 30,000 miles per hour, which meant it was in and out of the system in less than a day. Everything we learned from that mission came from that single flyby. James Webb, on the other hand, can observe Pluto whenever scientists schedule the time. It can go back again and again, building up a long-term data set that tracks changes over months and years. In fact, there are already plans for follow-up observations to see how Pluto's atmosphere and surface continue to evolve. Over the next decade, we might build up a time-lapse view of Pluto's seasonal cycle, watching this distant world change in real time. How incredible is that? But let's zoom out for a moment and think about what this means for the bigger picture. James Webb wasn't built specifically to study Pluto. It was designed to look at the earliest galaxies in the universe, to study star formation, to analyze exoplanet atmospheres, to peer into the cosmic dark ages. The fact that it can also revolutionize our understanding of a dwarf planet in our own solar system is just a bonus, a testament to how versatile and powerful this instrument really is. And it raises an exciting question. If James Webb can do this for Pluto, what else can it discover in our solar system that we haven't even thought to look for yet? Could it analyze the atmospheres of Neptune and Uranus in new ways? Could it study the geysers on Saturn's moon, Enceladus, or the subsurface ocean of Jupiter's moon, Europa? The answer is yes, and scientists are already planning those observations. This is the golden age of space exploration, folks. We've got rovers on Mars, a helicopter flying in the Martian atmosphere, probes studying asteroids, spacecraft orbiting Jupiter and Saturn. And now the most powerful space telescope ever built, revealing secrets across the entire universe and right here in our own cosmic backyard. And the best part? We're just getting started. James Webb has been operational for less than 2 years, and it's already rewriting textbooks. Imagine what the next 10 years are going to bring. If this video is getting you as pumped about space as I am, do me a huge favor and share it with someone who'd appreciate it. Send it to your friend who's into science, post it on your social media, help spread the word about what's happening out there in space. The more people who know about these discoveries, the more support there is for future missions. And honestly, the cooler our collective future becomes. So what happens next with Pluto? Well, the data from James Webb is still being analyzed. Scientists are comparing it with the New Horizons dataset, running new models, testing hypotheses, and preparing follow-up observations. There will be papers published, conferences held, debates among planetary scientists about what it all means, and gradually, over the coming months and years, a new picture of Pluto will emerge. It'll be more detailed, more accurate, and almost certainly more surprising than what we understood before. That's how science works. It's not about having all the answers right away. It's about asking better questions, gathering better data, and being willing to change your mind when the evidence points in a new direction. And here's the thing that really blows my mind. Everything we're learning about Pluto, this tiny world at the edge of our solar system, has implications far beyond just one dwarf planet. It tells us about how planetary atmospheres work in extreme cold. It tells us about surface chemistry on icy worlds. It tells us about the long-term evolution of bodies in the outer solar system. And all of that knowledge applies to the thousands of exoplanets we're discovering around other stars. Some of those exoplanets are ice worlds too, orbiting far from their parent stars in cold, dark regions of their solar systems. Understanding Pluto helps us understand those distant worlds we'll probably never visit. It's all connected. Every discovery builds on the last, and the puzzle of how planets and solar systems work becomes a little clearer with each new piece of data. Before we wrap up, I want to leave you with this thought. Pluto is about 3.7 billion miles away right now. The light reflecting off its surface takes over 5 hours to reach us here on Earth. When you look at images of Pluto, whether from New Horizons or data visualizations from James Webb, you're seeing the past. You're seeing what Pluto looked like hours ago, frozen in time by the speed of light. And yet, that distant world is teaching us things that matter right here, right now. It's expanding our understanding of chemistry, geology, atmospheric science, and planetary evolution. A frozen dwarf planet billions of miles away is making us smarter, more curious, and more capable of understanding the universe we live in. If that's not amazing, I don't know what is. The Space Frontier is all about bringing you these stories, these discoveries that remind us how incredible our universe is and how much there still is to explore. We've got videos coming up on James Webb's latest findings from Neptune, the strange signals coming from deep space, and the new missions NASA is planning to the outer solar system. You're not going to want to miss any of it, so make sure you're subscribed and hit that notification bell so you never miss an upload. And seriously, drop a comment below and let me know what you think about Pluto. Should it be a planet? Are you Team Pluto? Let's talk about it. I read every comment, and I love hearing what you all think about this stuff. Thanks for watching, and I'll see you in the next one. Keep looking up.